In this video, we're going to cover section 2.6, derivatives of inverse functions. So let's remember a few things about inverse functions to start off with. Here we have a graph of an inverse, or a function and its inverse. Here's f of x. This is f inverse of x. Remember that a graph reflected across y equals x gives us the graph of the inverse. And we notice at this point, AB corresponds to this point, BA, where we switch the x and the y. Hopefully you remember from pre-calculus when we did that, we would switch the x and y on the graph, the table, and the rule to find inverses. Before we move on to the theorems and the explanation, I would just like you to see visually what's going on. So we're going to take the derivative of inverse functions, and so what's going to happen is we have this. Let me try drawing that again. We're going to find the derivative at this point, and again that's the slope of the tangent line. Then we're going to find the derivative at this point, and we're going to see how they correlate. So again, there is a relationship between the slope of the tangent line, or the derivative, at AB and on the inverse at BA. And I'm going to show you how to find this analytically. First, let's take a look at Theorem 216, continuity and differentiability of inverse functions. Let f be a function whose domain is an interval I. If f has an inverse function, then the following statements are true. So remember, not all inverses are functions. So we're assuming that f has an inverse function, which means we're not dealing with like a parabola because it doesn't pass the horizontal line test. Remember, that's just a way to visually see, would this have, or would the inverse of this function also be a function? And more accurately, we would say that it's a one-to-one function. So if f is continuous on its domain, then the inverse is continuous on its domain. And if it's differentiable on an interval containing c, and f prime of c does not equal 0, then the inverse is also differentiable at c. So we have a function and its inverse. If this is continuous, that means this is continuous. If this is differentiable, then that means this is differentiable, as long as the derivative does not equal 0. Okay, and just visually we could look at that. The derivative of 0 means that we have a horizontal tangent line, which means it's got to be going back up, which means that our inverse would not be a function anyway. Okay, Theorem 217, the derivative of an inverse function. Let f be a function that is differentiable on an interval. If f has an inverse function g, then g is differentiable as long as the derivative at that point does not equal 0. Moreover, the derivative of g of x equals 1 over f prime of g of x. Okay, now this looks a little bit complicated, and there are some steps to the process, and as long as we remember the steps, this is not a difficult process, even though it seems to be confusing. So we're going to change this question a bit. We're going to skip the first one and we're going to do the second one, just to show this is the whole process. So we're going to take, what's the derivative of the inverse of f when x equals 3? Oftentimes that will be written as the derivative of the inverse at 3. Sorry, not x, but 3. Okay, that's what we're looking for. To do that, remember, we have a function and its inverse, and I want to know the corresponding parts, the corresponding points associated with this problem. Well, I want to put 3 into the derivative of this function. So that means 3 is my x value that I'm concerned about on the inverse. Okay, well, that means that it's the y value on my original function. Okay, and I am looking for this number here. Okay, so what we're going to do is we're going to take this equation f of x and we're going to say, well, when does 3 equal 1/4 x cubed plus x minus 1? There are a couple different ways to do this. One of the most straightforward on a difficult problem would be to graph it, graph f of x and graph y equals 3 and see when they intersect. For a lot of the problems that you will be given, it is actually not that difficult. We're dealing with a whole number. So oftentimes our x's will be -2, -1, 0, 1, 2, 3, things like that. Now, I'll give you an opportunity to graph these and check that way. But on this one, we're going to see that I think 2 cubed times 1/4 plus 2 minus 1 does in fact equal 3. So this x value is 2 and this y value is 2. That's kind of like a side problem to help us set up the initial problem. Because now we're going to take the derivative of the initial function, which is 3/4 x squared plus 1. Okay, now I can put my 2 in here, so we're going to find f prime of 2, and that is 3 plus 1, or 4. Now I have everything I need to plug it into this formula. And let's look at what we actually do. We're going to take 1 over f prime of g of x. Well, g of x is the y value of the inverse, so that's like our f inverse of x. So this is actually this number 2, but it's also this number x. So I'm going to take f prime of 2. Well, I just found f prime of 2, so all I have to do, the derivative of the original function is 4, and so the derivative of the inverse function at our point that we're concerned about, 3, is 1 over 4. Okay, so let's recap this process, and then we will do it again. I like to start by writing these parentheses and finding these 2 points, finding these corresponding points. Then you take the derivative of the original, and put that x value in. Then you put 1 over that number. That's the derivative of the inverse. Okay? So example 2 says inverse functions have reciprocal slopes. So again, let's take a look. I have a function and I have its inverse. The function at 0.23 corresponds with the inverse at 0.32. And the instantaneous slope, or the derivative, at these points, let's put an e there so we're not dealing with slop. So the instantaneous slope at this point is 4, and the instantaneous slope at this point is 1/4. That's the relationship we need to remember. And we'll do some practice to help us with that process. So let's do one more problem here. This isn't in your notes, so you're just going to have to add it, try to find some empty space. So we'll call this example 2.a. So here is our function, f of x equals 3 minus 4x cubed. And we want to find the derivative of the inverse function at -1. Okay? Now, this could have been asked to say, evaluate the derivative of the inverse of x when x equals -1. We're just going to plug that in. Okay? So let's go through the process. I'm going to say, here's my function, here's my inverse, and I'm going to create my 2 corresponding points. Whatever value we're given for the x of the inverse, we put here and here. Now we'll use the original function to find x. So negative 1 must equal 3 minus 4x cubed. Okay, if I solve this, I'm going to subtract 3 from both sides. Negative 4 equals negative 4x cubed. That means 1 equals x cubed. So x equals 1. So I'll put 1 here and here. Now I have my corresponding points. Okay, so this work is done. I can ignore that. Now I need to find the derivative of f at 1. So f prime of 1 equals negative 12x squared. I should probably just put an x there. So f prime of 1 equals negative 12. So to find the derivative of the inverse function at negative 1, my final step is to go 1 over negative 12. And that's my answer. So again, we found the derivative at the first corresponding point, and we used the reciprocal to find the derivative of the inverse at the corresponding point on the inverse of the graph. Now, derivatives of inverse trigonometric functions. This is a little bit more complicated, although you just have some rules here that you follow and you recognize, okay? So arc sine, please note that's kind of like the sine of the inverse of u. So that's inverse sine. Usually arc sine is used so that we don't get confused with a negative exponent. Okay? So arc sine of u is, there's the derivative of our inner function, because this is allowing us to use the chain rule. That's the derivative of the inner function over the square root of 1 minus u squared. Arc cosine is negative u over 1 minus u squared, square root of 1 minus u squared. And then we have arctangent, cotangent, secant, and cosecant with various formulations of 1 minus u, 1 plus u, u squared, square roots, and all of that. So let's look at how we would use this. So example 4, the derivative of arc sine of 2x. So what I really want to do is let's identify our u. Our u is 2x. Okay, so I'm just going to reference this formula up here. So again, the derivative of that inner function is 2 over the square root of 1 minus u squared. Now because we have u squared, so u squared, that's 2x squared. That would be 4x squared. So you either have to write it this way with parentheses or this way after squaring the 2. So I'm going to write 1 minus 4x squared. That is the derivative of the arc sine of 2x. Okay, now let's do the arctangent of 3x. So in this case, u equals 3x. So it says do the derivative of the inside, that's 3, over 1 plus, again we have u squared, so 3x squared would be 9x squared. And that's the arctangent, derivative of the arctangent of 3x. Derivative of the arc sine of square root of x. So that is u equals square root of x. So the sign says the derivative of u on top. So the derivative of square root of x is 1/2 x to the negative 1/2. That's all the derivative of that inner function. Okay, over the square root of 1 minus our u squared, but square root of x squared is just x. So we could rewrite that as 1 over 2 square roots of x times the square root of 1 minus x. Now we have arc secant of e to the 2x. Again, I'm just going to be following this rule at the top of the screen. my u will equal e to the 2x. Now notice I kind of have a u and I kind of have a v if I'm doing chain rule, right? So I could change that 2x to a e to the v, and my v is 2x. So I have u prime, so I got to take the derivative of that inner function, 2 times e to the v, which is 2x, because the derivative of that outer function is just e to the v, okay, over the absolute value of u, that's e to the 2x, although it will always be positive, so I will drop the absolute value in the next simplified form of this. Then I've got u squared, so e to the 2x raised to the second power minus 1. So this should give me, well, this e to the 2x and that e to the 2x are going to cancel, again, because this is always positive. So 2 over the square root of e to the 4x, remember 2x squared, we multiply those exponents minus 1. And that's the derivative of the arcsecant of e to the 2x. So you now know how to find the derivatives of inverse trig functions using these. And again, the process for finding the derivative of regular inverse functions, starting with finding the corresponding points, and then taking the derivative of this x value, and then doing 1 over. And that's the process, and we'll have additional practice in class. Thank you for watching.